per day, 180 liters of filtrate are formed by our kidneys, but only 1 to 2 liters are excreted out. So, why and how does kidney do all of this? How does it decide which one to keep and which one to not keep? And when I ask this to my students, they immediately say, "Oh, ma'am, you know, tubular reabsorption. There's nephron, and the tubules reabsorb all of the water and ions through it." But really, is that the first thing that happens? I mean, try to visualize anatomy and physiology. What is, try to, you know, trace down the path of a water molecule or any molecule. What is the first thing that it encounters in the kidney? Is it really tubules? So, the answer to this question is explained, and it is explained by today's topic, which is glomerular filtration membrane. It'll just be a short class, you know. So, the following topics will be covered under this. First is introduction. Then a little bit about the layers. Third is factors affecting the membrane. Then few clinical examples and a short summary. So please be with me. Okay. So first we come to the introduction. Let's just take a brief overview, a holistic overview. Where exactly is the membrane? We all know it's nephron, but where exactly is it, and how in the overview of a body? So kidney has to, you know, kidney has a tough job. It has to it has to remove unwanted substances, it has to remove toxins, it has to regulate BP, it has to regulate osmolarity, it has to do everything. So all the blood, a big job. So all the blood passes through kidney. And what is the functional unit of kidney? Nephron. This nephron has a glomerular membrane. From this membrane, a filtrate is formed. The 180 liters I was talking about, and from that the filtrate goes into tubules, reabsorption, and then urine is formed. So this is where the membrane fits into the body. Now students must be wondering, by the way, this class is not just for medical students, it's for anyone who's interested. So glomerular membrane, so this is where the membrane fits into the body, and most students must be wondering, why is ma'am taking this one tiny membrane and doing a whole lecture about it and going on and on and on? But we need to realize that this tiny membrane forms the first checkpoint of water, ions, various unwanted substances. This is Mr. Guard, the first Mr. Guard that toxins encounter and unwanted substances encounter, even various ions and molecules. So that is why it's very important to study this very tiny but highly specialized membrane, and in fact very important membrane. So coming to the layers part, layers. Okay, so kidney has, no, it's not kidney, glomerular filtration membrane has 3 layers. and these layers are. So let's trace the path of a water molecule. What will it first encounter? So the order, the diagram that I'm going to draw, the orientation or the direction will be this. So first the water molecule will encounter a capillary endothelial cell layer. Then visceral layer of Bowman's, not visceral layer, basement membrane. This is basement membrane. And the innermost is capillary endothelial cell. And the last one is visceral layer of Bowman's capsule. It has something known as a very important cell known as podocytes. Podocytes contain something known as, it's a foot process. So the foot process of the podocytes form something called as filtration slits corresponding to a size of 25 nm. So these filtration slits decide which molecule is going to go or not to go. Moreover, the capillary endothelial cell has a pore size of 60 to 70 nm, and the basement membrane has no pores but corresponds to a permeability of 8 nm. So 60 to 70, 25, 8 nm, which is the limiting layer. It is the basement membrane. So basement membrane decides, according to the size of the substances, which molecule to pass and which not to pass. But things are not as simple as it seems, and we'll discover more things as we go by. But just so you know, there are three layers: capillary endothelial cell, basement membrane, and visceral layer of Bowman's capsule, which has a highly specialized cells known as podocytes, which helps in the structural integrity of the membrane, as well as forms its foot process forms a filtration slits which corresponds to a size of 25 nm. Okay, so layers are over. Now coming to factors. Now coming to factors affecting filtration through the membrane. Coming to the factors, now let's just take two important personalities in our body, although there are many important personalities, but let's just take two. First is, can you guess? This is Mr. Albumin, and this is Mr. Glucose. Mr. Albumin and Mr. Glucose are in a race. The race to pass through the glomerular membrane. Now the glomerular membrane says, hey look, I have no problem with both of you. I have no personal grudge, but I can let you pass, but both of you should fulfill two criteria. And they ask what? So first, we already know it's pore size. For a molecule to pass through, it should correspond to a pore size of 4 to 8 nm. Below 4 are freely filtered and above 8 are not that much. So the optimum range is 4 to 8 nm. So Mr. Albumin says, Mr. Glucose, you lose. I can cross through it. But the membrane says, hey, you didn't listen. I specified that there are two checkpoints. One is pore size and second is electrical charge. I am lined by glycoproteins which are negatively charged, and we all know chemistry, negative and negative repels. So I'm specifically looking for a cationic molecule which is positively charged, and then Mr. Albumin's face drops, you know, because Mr. Albumin is unfortunately negatively charged, and Mr. Albumin loses, and Mr. Glucose, which is electrically neutral and has pore size, it is relatively fulfilling the pore size of 4 to 8 nm, and Mr. Glucose gets a pass, Mr. Albumin loses, Mr. Glucose wins. So for a molecule to pass through, the molecule should fulfill the pore size as well as be positively charged, and the glycoproteins are lined by negatively charged molecules known as made up of sialic acid. Now we come to a famous graph which is important in your exams also, and I don't know why students, whenever they encounter a graph, they become tense or they get scared. Just read what is the relationship between x and y axis, and the graph just tells a relationship between two or more variables. So don't be afraid of it. So this is the graph where in x axis we have the effective diameter, and in the y-axis we have the fractional clearance. I'll just draw and then I'll explain you. Cationic neutral So this graph tells a relationship between cationic, neutrals and anionic modules. And in the x-axis we have effective diameter, and in the y-axis we have a fractional clearance. Now we see that no matter what the diameter of a molecule is, if it is cationic, it is preferred more than anionic. If the diameter is less, then you can see even anionic molecules get filtered, but as it approaches to 8, they stop, their filtration decreases. So from this graph we can conclude two things: charge matters at cationic are more preferred than neutral or anionic, and as well as diameter also matters. The molecule which falls between effective diameter as well as the charge gets a pass, and that's why Mr. Albumin, sad Mr. Albumin, didn't get a pass because he didn't fulfill the charge criteria. He was negatively charged. The proteins are lined by negatively charged glycoproteins containing sialic acid, and that's why albumin didn't get a pass. Okay, so this is a very famous graph and it often comes in exams. What about the clinical things, when we talk about disease, it gives us a perspective of why certain things, even though they are very, very tiny, are so important. So, first is first clinical condition, glomerulonephritis. What does itis mean? Inflammation. So inflammation of the membrane, and if the membrane is inflamed, it can't work properly. Who gets a pass? Mr. Albumin gets a pass, and Mr. Albumin is a plasma protein. So there will be proteinuria, and as well as RBCs get a pass. So hematuria. Second, what could be the second condition? Minimal change disease. Here the problem is in the negatively charged glycoproteins which line the membrane. So again Mr. Albumin gets a pass. So here also proteinuria will be there, selective proteinuria. So these are the two conditions, just to give you a perspective of how this membrane is so important. Now summary, a little short summary. So glomerular membrane is the first checkpoint that any molecule will encounter if that molecule is about to get undergo the process of filtration, which is virtually all the cells in our body. And it is its layers is capillary endothelial cell layer, basement membrane, and visceral layer of Bowman's capsule, and it is governed by two factors: pore size and electrical charge. Thank you.